Hello, students. As you know, we are continuing with our brightest topic of the year, stars. And yesterday we talked a lot about some different kinds of stars in terms of their relative sizes to one another. Well, today we're really going to get into the meat of this topic in terms of it being the brightest topic of the year, because we're going to be talking about the brightness of stars. Before we get to star brightness, however, we are going to first discuss the temperature of stars, because the temperature of stars is what really indicates the surface temperature of a star. So let me try to explain this as you're copying this in your notes. Star temperature. The star color indicates the surface temperature. Now, I think we all know that stars are pretty hot stuff. That's right, they're hot. They are burning balls of hydrogen and helium gas. We discussed that yesterday. And we also talked a little bit about nuclear fusion reactions and just how much energy is being released by a star. It's pretty much incomprehensible to the human brain as to how much energy is being released. But not all stars are the same. Some stars are more massive than others, and a different fate awaits them, as we will learn this lesson. And some are bigger, some are smaller, and they're different colors as well. Now, this may come as a surprise because many people, if they live in an area where there's a lot of light pollution and they look up at the night sky, you might be tricked into thinking that all the stars are just white points of light. That is not the case. If you live in a darker area and you're more observant, and even with the unaided eye looking at stars, you can tell that some stars are different colors. Yes, there are a lot of white ones, but there are also some red ones. And there's a red star in the night sky that you can see. Rigel and Betelgeuse, those are examples of stars that are not white. There are other stars that you can more easily see their color by using binoculars or a small telescope. You can make out the fact that not all stars are the same color. Now, where are we going with this little discussion of the color of stars? Well, how many of you have ever seen something burning? Probably most of you, right? How many of you have ever heard the expression, boy, that is red hot? Yeah, I'm sure you have. How many of you have ever used a toaster or a toaster oven? And you turn it on, you put some bread in there or a bagel or something, and you're toasting it, and you see the little heating elements, the little coils, little wires in there, turn red hot. Well, red, that color that our eyes see, is an indicator of the temperature at which that little element is burning. Now, in 8th grade, we're going to be using Bunsen burners. But even if you've never used a Bunsen burner before, if you have a gas stove or know someone with a gas stove and you've ever turned on the heating mechanism and you see the flames shoot out, you want a nice blue flame. A blue flame has a certain temperature to it. I'm sure you've seen candles. I know you've seen a candle lit because we light a candle here every time we have a birthday. A candle flame is yellow. So we have these different colors associated with different luminous bodies that are burning or very hot. Those different colors indicate different temperatures. We don't have to feel it to know if it's red hot. You know, if you see something glowing red, you're not going to touch it or you will get burned. Back to stars. The surface temperature of stars is a lot lower than the core temperature of a star. When we get to our next topic of the sun, we're going to talk about the guts of our own star, and we'll see how the core of a star, like our own sun, is millions of degrees, which is required for that nuclear fusion to take place. But that energy disappears a little bit as it reaches the surface of the sun. And it's only the surface of the sun or the surface of a star that we see when we look at it with visible light. So let's get to this chart. There's a distribution of different colors that relate to different temperatures. The hottest stars in the universe are those that appear blue in color. Blue stars have a surface temperature of about 35,000 degrees Celsius. That's hot. White stars are a little bit cooler than blue stars, but still very hot at the surface. White stars have a surface temperature of about 10,000 degrees Celsius. Still, that's pretty hot. Yellow stars, like our own sun, yellow stars have a surface temperature of about 6,000 degrees Celsius. And I know on this slide it might be a little bit difficult for us to actually read this number. Let's see if I can do something here. And no, it'll take me too long. So this is yellow stars have a temperature of about 6,000 degrees. You can write that down. And by the way, white and yellow stars are most common in the universe, at least as far as we have seen so far. Red orange stars are those with a surface temperature of about 5,000 degrees. And finally, red stars have a surface temperature of about 3,000 degrees. Now, if you look in your notes from yesterday and you compare the relative sizes of stars from yesterday and the surface temperatures from today, you might actually make a relationship, see a relationship or make a connection between the temperature, surface temperature of a star and its size. Can anyone make a relationship, state a relationship between the relative star size and its surface temperature? If you said that the red stars or the cooler stars are larger than the hotter stars, which are smaller, you're absolutely correct. There is a relationship. The bigger the star, the cooler it gets because typically its size increases towards the end of its lifespan. But we'll talk more about that after we finish discussing brightness, because there's two different kinds of brightness that we have to talk about here. When we talk about star brightness, we're going to begin with what's called the absolute brightness or the magnitude of a star. So here's the deal. How many of you have ever changed a light bulb? If you've ever changed a light bulb and you wanted to put the same kind of bulb back into a socket that has had a bulb that burned out, how do you know what kind of bulb to put in if you want it to give off the same amount of brightness? Well, you look at the wattage. You look at the wattage. So if you've got a 100 watt bulb in your socket and you want to replace it with a light that gives off the same amount of light, you find another 100 watt bulb to replace it with. And a 100 watt bulb and a 100 watt bulb, they give off the same amount of light. Think of that in terms of a star. The absolute brightness, also called magnitude, is the light that is actually given off. So if you're looking at a light bulb, like this one here, if you're looking at a light bulb and it's a 100 watt bulb and you turn it on, it's going to be producing 100 watts of light. Now that might translate into another unit called lumens, which is a measure of exactly the brightness, but hopefully you get the idea. And I think you'll get the idea even more when I discuss the second type of brightness. But first, a question. Let's say you take this light bulb and you are right up next to it, and it's a 100 watt light bulb. It's going to be pretty bright, right? Now, what if that same 100 watt light bulb was on the opposite side of the laboratory as you, and you looked at it? Would it be as bright? Would it be brighter? Or would it be dimmer? Which would it be? Hopefully you said dimmer. In fact, in the lab, you'll see that this week, that the farther away you are from a light source, the dimmer it appears. Think about driving at night. How many of you have ever been in a car driving at night? Now imagine it's a lonely highway and you're driving down a dark road, and in the distance, you see a car coming the other way. You first make out the dim headlights of that car, but as it gets closer to you, what happens to the brightness of those headlights? Do they get brighter? Do they get dimmer? Or do they not change? The car is getting closer. What happens to the brightness of those headlights? I'm sure you knew the answer. They get brighter. But now I want you to think about this a little bit more. Did the headlights change? Did the driver of the other car change the strength of the headlight light bulbs as it got closer to you? No, of course not. At least hopefully not while they're driving. But why did the brightness appear to get brighter as the headlights got closer to you? Any idea? Because they were getting closer to you, they appeared to get brighter. And this is the second type of brightness. Apparent brightness. The apparent brightness of stars is the light that is actually observed by someone. Remember, not all stars are the same distance away from us. We already have established that there are different kinds of stars. Scientists like to group them into different categories, and that's important. And if you have two stars that have the same qualities and characteristics as one another, but one of them is closer and one of them is much farther away, which one do you think is going to be brighter? The one that is closer to you will be brighter than the one that is farther away. Why? Because even if they're identical sizes, identical absolute brightnesses, if one is further away than the other, the one that's closer is going to be brighter, just like the headlights. Now, this is a very, very important concept in astronomy. This difference between absolute brightness and the apparent brightness. Because we don't have tape measures long enough to measure distances to stars. We've never we'll never be able to travel to different stars, but we can learn a lot about stars. As you know already, we can learn about their composition based on spectroscopes without ever having to take a sample from a star. But there were a couple of astronomers, one of whom had a very painful name. His name was Hertzsprung. Hertzsprung and Russell recognized some very important relationships between the brightness of a star and the temperature of a star. And knowing a relationship, recognizing a relationship like you observed at the beginning of the period, recognizing a relationship between the color of a star, the brightness of a star, you can learn a lot more about stars, the distances to stars, the age of a star, the health of a star. You can tell a lot about stars by knowing a couple important pieces of information. And so these scientists, Hertzsprung and Russell, developed a diagram. And it's a diagram that scientists use today frequently. And this diagram relates two things between stars. It relates the absolute magnitude and the surface temperature of stars. Now, let me try to explain why this is so important. Although, if you think about it, you already know the reason. Think about the headlight example, okay? By the way, how many of you have ever noticed cars with headlights at night, that the headlights are different colors? Have you noticed that? Some headlights, the light coming out of the headlights is a little yellowish. Some are white. Some have a blue tint to them. Some of the newer headlights have a blue tint. There's a reason for that. There's a different element in those headlights. And the elements, whether it's argon, krypton, xenon, or nitrogen, depending upon what element is in those headlights, they burn, the filaments burn with a different temperature, just like stars. And those different temperatures we see with our eyes as being a different color. That color tells us something with stars about the surface temperature. So looking at the color of a star, Hertzsprung and Russell knew, the color tells us about the surface temperature. Now, in studying thousands and thousands of stars, they were able to make another relationship between the surface temperature of a star and what its absolute magnitude would be. Now, this is important for another reason. The absolute magnitude is like reading the number of watts on a light bulb. It gives off a certain amount of light. We call that the absolute magnitude. But here's the deal. If the light bulb is closer to you, it's brighter. If it's farther away, it's dimmer. Color doesn't change, but its brightness does. So if you know the wattage of a light bulb and it's far and far away from you, and you measure its luminosity, or how much brightness you are observing, the apparent magnitude, there's a mathematical relationship between the apparent magnitude and distance. You intuitively know this if you've seen headlights from a car getting brighter as that car gets closer to you. But if you observe that enough and you make measurements, scientists have come up with a mathematical equation. So in other words, If you look at the surface temperature of a star, in other words, what color is it? You know the surface temperature. And you measure the absolute magnitude, but you know what the absolute magnitude is based on the color of the star. And you measure the apparent magnitude, you plug in some numbers into an equation and you can determine how far away that star is. That is a really, really cool thing about astronomy. We can use mathematics to help us discover things in the universe, places that we can't even get to. We can explore the universe with math. So the next time you see your math teacher, thank them for teaching you math, because math literally is the language of the universe, and it can help you learn a lot about the universe. Now, you don't have to copy this down. You have a similar diagram in your notes, but I want to show this HR diagram to you. Here's the temperature on the x-axis. Here is its luminosity or absolute brightness on the y-axis. And this is the distribution of stars as they appear in the universe and as they are plotted on the HR diagram. And you have this similar diagram in your book, which you can label. And I've identified different regions of the HR diagram, A, B, C, and D. A, this region is comprised of supergiants. B are the giants. C are the main sequence stars. And right in the middle, smack dab in the middle, I put an extra star there because that's special. That's where our sun is. Our sun is a medium-sized main sequence stars. It's middle life. It's average by all accounts, except for the fact that it's ours. And finally, in the bottom of the HR diagram are the white dwarfs. Now, I want you also to pay attention to these arrows here. The brightness on the y-axis increases from bottom to top. Brightness increases, so the brighter stars are higher on the chart. Temperature increases as you go from right to left, from right to left. So hotter stars are on the left, cooler stars are on the right. And check it out, the white dwarfs are over on the right. The red giants are over on the right. Temperature increases from red to blue. And that's important for you to know. Now, we're going to finish up today with a couple more things, starting with the life cycle of a star. Let me take you through this diagram quickly here. The life cycle of a star. The formation of stars begin with what's called a nebula. A nebula is a big, massive cloud of dust and gas, all having mass. And as we know from previous topics, any object with mass exerts a gravitational influence on other objects with mass. And so all of this dust and gas will be attracted to one another. If there's enough dust and gas, it will condense into a nucleus, which will have such an incredible density that it will ignite nuclear fusion, and we have the formation or the birth of a star. Now, depending upon the mass, that star is going to go through its lifespan. Most of its life is spent as a main sequence star, like our own sun here. But depending on its mass, it will suffer a different fate. Eventually, when it starts running out of fuel, will develop into a giant or a supergiant star. If its mass is relatively low after it explodes, it will then turn into a white dwarf star that's very small. And then eventually, when its fuel is completely spent, it will end its life as a dead star, sometimes called a brown or black dwarf star. And what might that star look like? It actually might look like the planet Jupiter, to be honest with you. But a dead star, it no longer shines on its own. However, if a star is a supermassive star, it's got a lot of mass, its fate is quite different. A supermassive star will explode as a supernova, which can be seen across the universe. And if it's got a lot of mass, it may end its life as a neutron star, which is like a blinking beacon, like a pulsar in space. That neutron star isn't any larger than the size of a town on planet Earth. But if it has super, very high mass, the most massive of stars, after they explode, they will implode, meaning they will collapse on themselves, and their end is a black hole. Now, a black hole is not a hole at all. It is a super massive, high density object in space with so much mass and so much gravitational pull. It is currently believed that there is a black hole in the center of most, if not all, galaxies in the universe. It's so massive that it holds the galaxies together. We have a black hole in the center of the Milky Way. But if you ever see a picture of the Milky Way, it seems to be very bright near the center. The reason for that is because the black hole in the very center has so much mass, it is attracting so many other stars that orbit around it, that we see this massive body of billions of stars orbiting the black hole. But it is believed that many of these stars eventually get sucked into the black hole and add to its mass. We could talk a lot more about black holes, but right now let's finish with this slide, which is a summary of what's called stellar evolution. Stellar evolution is the life cycle of a star, which we just talked about. It begins with the formation of a star, and you could be writing down the red, bolded, underlined words here. But star formation is how all stars begin from a nebula, a big cloud of dust and gas. Most stars will spend their lives as a main sequence star as they burn their fuel. And then ultimately, it is the mass of the star that determines its fate or its final stages of life. And those final stages, the end of the life of a star, can result in either a black hole, a neutron star, or a dead star, also known as a brown or black dwarf, depending on its mass. So stars are very dynamic. We are able to observe stars undergoing different points of their life cycle, which is how we know the life cycle of a star. It's a fascinating topic, and we're not done yet, because tomorrow we're going to be talking about the location of stars, and we're actually going to learn a cool technique called the parallax method, another method that astronomers use to measure distances to stars really accurately. In fact, we are going to measure the distance to a star tomorrow in the laboratory. But until that time, I'm going to say bye-bye.